Hello, I'm Samson Rainey with NASA's Earth Science News Team, and welcome to Hangar 703 at NASA's Armstrong Flight Research Center in sunny Palmdale, California. You know, in its time, NASA has accomplished really big things, such as sending humans to the moon, putting rovers on Mars, and looking out into the deep recesses of the universe. But there's another big accomplishment that hits really close to home, and that's NASA's fleet of Earth-orbiting satellites. For decades, scientists have used these satellites as their eyes to observe how our planet is changing, from weather and climate across the globe to fires, our oceans, forests, agriculture, even the air that we breathe. But sometimes we need to take a closer look to get a better understanding of how our planet's working, and that is the purpose of NASA's Earth Science Field Campaigns. Under NASA support, scientists get up close and personal with their subject matter, making observations and gathering measurements in order to unlock new understanding of how our world works. Today, we are giving you a taste of 5 new airborne campaigns headed into the field this year with NASA aircraft in tow. Competitively selected, these multi-year funded campaigns called Earth Venture Suborbital Missions, were chosen for their potential to not only better understand the current state of our world, but also to predict change. And this year's class is all-American. That's right, all the campaigns are based out of the continental United States. So without further ado, let's preview those 5 campaigns. Starting from the West Coast. Out of NASA Ames in Silicon Valley, the Submesoscale Ocean Dynamics Experiment, or SMODE, is deploying airplanes, a ship, and a fleet of autonomous platforms 200 miles off the coast of San Francisco to study how swirling currents of water called eddies play a role in the exchange of heat between ocean and atmosphere. From Salina, Kansas, dynamics and chemistry of the summer stratosphere, or DCOTS, will fly high with NASA's ER-2 aircraft to investigate how strong summertime storms that punch into the stratosphere change its chemistry, including ozone. Flying out of New Orleans and NASA's Johnson Space Center, NASA aircraft will join researchers on board for the Delta X mission to observe the interactions between water and sediment in the Mississippi River Delta to get a better handle on why some parts of the Delta are disappearing and others are not. From Langley's Research Center in Hampton, Virginia, NASA aircraft with the aerosol cloud meteorology interactions over the Western Atlantic experiment, or ACTIVATE, will maneuver in and around clouds to identify how tiny particles called aerosols interact with them and influence weather and climate. And lastly, as part of the investigation of microphysics and precipitation for Atlantic coast threatening snowstorms, or impacts, aircraft based out of NASA's Wallops Flight Facility on Virginia's eastern shore will fly head-on into snowstorms to investigate how the most intense snowfall is formed in order to improve observations from space and ultimately improve weather forecasts. And with winter upon us across much of the country, we think that impacts is probably the best place to start. And welcoming onto the stage is Lynn McMurdy, who is the lead scientist for impacts. She's also an atmospheric scientist at the University of Washington. Thanks for joining us, Lynn.
It's great to be here.
So we're looking at unraveling the mysteries of these bands of snow in clouds. Could you tell us a little bit more about that and how you're going about it?
Sure, I'd be happy to. So as you know, snowstorms are fairly large, and the cloud systems with them span hundreds and hundreds of miles. But what's really interesting is the snowfall within these large areas of clouds are not evenly distributed. They are often organized in narrow bands of high snowfall amounts. And this is what we're trying to investigate, is the processes that contribute to this banded structure and how it varies from storm to storm. Some storms don't have the bands and others do have a lot of them. And we are studying this on multiple scales, from the larger scale down to the microphysical scale, the scale of the snow crystals themselves. And they vary a lot. They vary in shape and size and amount. And the snow crystals are one of the key features that we are studying in impacts.
Wow, and my understanding is you're the first campaign up this year, so you're heading out next week, right?
I am heading out next week. Yes, we are the first campaign to start. Actually, in 2 days, I leave for Wallops. We are going to be flying an aircraft that you will be seeing later on today, the ER-2. It's already equipped with all the instruments that I need for my campaign. The R2 is going to be flying high above the snowstorms themselves at altitude about 68,000 feet or 20 kilometers. It'll be equipped with remote sensing instruments that are the same as what we have on satellites, both radars and what's called radiometers. And below that, in coordination with the ER2, we will fly what's called the P3 aircraft. And it is lucky, it gets to fly in the snow clouds themselves. It's kind of bumpy sometimes because it's very turbulent, but they are equipped, it's equipped with instruments that measure the snow crystals that I talked about, and also the environment in which the snow crystals form, so the environmental conditions. And we'll also do what's called a drop sonde and measure the profile of temperature and wind.
So the point of the two aircraft again, so that you need one that's going through the snow bands and the other one will be
above the snow bands. Right. So we need the coordination to help us understand how one measures from space. So the ER2 is simulating the satellite, and so we take measurements just like a satellite would, but then we measure inside the snow bands themselves so we can relate what's going on in the clouds to what is being seen above by the satellite.
Cool. Well, I think that anyone who's lived through a snowy winter can appreciate any effort to improve our snow forecasting.
I know.
But I'll let you, in your own words, why is this such important?
It's so important. Well, I'm kind of one of those people who think snowstorms are beautiful, and they are. The snow is a beautiful thing to see, and see trees covered with snow. But we all know it's also hazardous, especially hazardous for transportation and public safety. So it's very important to be able to forecast the amounts of snowfall, and that's what's really variable in these storms. We can't do that very well. We need to improve that, and the measurements we make and impacts will help us improve those forecasts. It'll also help us improve how we measure from space so that we can monitor storms all around the world, especially places that don't have information.
And real quick, Lynn, so what's the motivating factor for you? I mean, you have your snow earrings, you have your snow socks, you're a big fan of the weather, I see.
I am totally a big fan of weather. I've been watching the weather ever since I was really little. I do a lot of activities, and in order to know when and where to ride your bike or go hiking, I need to do that. And so it's really exciting to be a scientist and be able to study these snowstorms and learn the details of the inside of the storms.
Well, thanks so much for joining us, Lynn.
It's been a pleasure to be here. Thank you so much.
Of course. So we caught up with my colleague Chelsea Bayarte, who actually went to visit your teammates there as they prep for this flight happening next week, and she's going to show us what it's like to fly in one of these NASA science aircraft.
That's great. Yeah.
Awesome. So take it away, Chelsea.
Thanks, Samson. We're here at NASA's Wallops Flight Facility on the eastern shore of Virginia, home to the P-3B, the aircraft that you see here behind me. This research aircraft, as well as NASA's ER-2, are going to be collecting data from the skies as early as next week. Let's go meet up with Deputy Principal Investigator for the Impacts Mission, Dr. John Yorks, who's going to tell us a little bit more about the instruments on board. Let's go. Okay, so we're here inside the P-3 aircraft. I'm here with Dr. John Yorks. How are you doing today?
Good. Hi, Lynn and everyone at NASA Armstrong.
So this research aircraft is totally outfitted with a bunch of scientific gear. What do we have on board today?
So Impacts uses cloud probes out on the wings of the P-3, and these cloud probes take high-resolution images of ice and snow particles, and we then use those images to determine the size, shape, and other properties of the particles. That data is then transmitted inside the airplane to computers, where scientists sit and monitor the data and the instruments. Another important instrument, if you follow us, is the drop sonde. Now, the drop sonde is a 12-inch tube, kind of similar to the tube in a paper towel roll, and it has sensors inside and a small parachute at the top. And we have an instrument back here, if you follow us, that actually acts a lot like a t-shirt cannon, and will shoot these drop sondes out into the atmosphere, where they fall through the sky at about 25 miles an hour and measure temperature, humidity, and wind speed. And all this data is important for determining the structure of snow bands.
So it seems to me like snowstorms are pretty difficult to predict. How will this data from the impacts mission help us understand them more?
So we're going to combine the data from both the ER2 and the P3, and when we combine all that data, we'll be able to improve the measurements from space of precipitation and also the model predictions of snowfall.
Very cool, thank you. So it seems like our science teams are ready, our instrument teams are ready. There's one more person we have to talk to before we get this mission off the ground, and that is our NASA pilot. So joining us here today is NASA pilot John Vacura. John, thanks for being with us. So what is it going to be like flying through these snowstorms?
Well, it shouldn't be too different than driving through a snowstorm. Now, generally pilots like to avoid things like turbulence, convective activity, and icing. And the winter storms, we won't have the convective activity you typically see in a summer storm, so we don't usually have to worry about the lightning and the hail like we would in the summer. But there will be turbulence, there will be winds, and there will be icing conditions. The good news is the P3 aircraft that we'll be flying has very robust anti-icing and de-icing systems. So our engines and our wings and our empennage will be protected. So we should be pretty good in most cases. So just keep an eye out and make sure we stay out of the worst areas.
So it seems like flying conditions, while difficult, may be okay for the pilots. What about the passengers on board? How will it feel taking this flight compared to a commercial flight that folks at home may have taken during the holidays?
It shouldn't be too different. There might be some areas that we're asked to fly in that are a little more turbulent than they would experience in a regular flight. But overall, it should be in pretty good shape. Just a good seatbelt and not walking around when they shouldn't be, and they should be okay.
Sounds good. So I have to ask, I'm curious, this is the coolest job in the world. How does one become a NASA pilot?
It is a pretty cool job. In general, most people get their backgrounds from the military, and that's because we fly a lot of different aircrafts here at Wallops and some of the other centers, and we fly in conditions that most people avoid. So they're looking for people that have a lot of experience and can kind of handle a wide range of flight conditions, and you're usually going to find that in the military.
Great. Well, thank you for joining us here today. From all of us here at Wallops, happy flying and best of luck during your mission. Samson, back to you.
Great, thanks so much, Chelsea. So we're moving on from East Coast snowstorms to intense summertime storms that breach the stratosphere in the Midwest. Joining us right now is Ken Bowman, atmospheric scientist at Texas A&M, who's also lead scientist for DCOTS, or Dynamics and Chemistry of the Summer Stratosphere. Ken, thanks so much for joining us.
Good morning, Samson. It's great to be here.
So I think it's interesting that most people find it surprising that while most of our weather actually happens in the troposphere, every now and then we have these really strong storms that kind of breach the stratosphere, and we're not quite sure what's going on there. Do you want to talk about the background on that and how you plan on investigating?
Sure. So as you said, most of the Earth's weather happens in the lowest layer in the atmosphere, which is called the troposphere. And above that is the stratosphere, which is very stable and very dry, and it also contains the Earth's ozone layer, which protects the Earth from dangerous solar radiation from the sun. But some storms are actually intense enough that they overshoot the top of the troposphere into the lower stratosphere, and they carry water and pollutants and particles and things into the stratosphere.
So I'm guessing you need specialized aircraft to get that high up, right, Ken?
Yes, so just like impacts, we're going to be using the NASA ER2 high-altitude research aircraft. It's really a unique platform for making the kind of measurements that we need to do. And unlike impacts, which is using remote sensing instruments, for our project, the ER2 will be carrying 12 different instruments to measure atmospheric gases and particles and meteorological parameters. And the plan of the project is to fly the aircraft through the outflow from these storms in the lower stratosphere.
So the big question is, why is this a pressing science question?
So the stratosphere is actually quite important for the Earth's climate, and of course it contains the ozone layer, which is vulnerable to pollutants when they get up into the stratosphere. So we're going to be studying the summertime stratosphere. There are a lot of things we don't know about the composition and the radiation and the dynamics of the lower stratosphere. And the main goal is to make sure we understand how the stratosphere works now, so that as the climate changes and the composition of the atmosphere continues to change, we'll be able to predict and better understand how the stratosphere might change in the future.
Cool. And so basically, I know that a lot of campaigns, scientists have some sort of idea of what they expect to find. Is this a case where it's a real discovery mission? You're not sure exactly what's going to happen. This is very novel results coming forward.
Yeah, this is the first mission that's really been designed specifically to look at these overshooting thunderstorms and what they put into the lower stratosphere. So we've seen glimpses of this on previous missions that happened to fly through the outflow from these storms. But we expect to be targeting these on almost a daily basis as they happen over the central U.S.
Cool. So, Ken, what drew you personally to this science? When you could have picked anywhere in the atmosphere to study, but you're focused on this area. Why is that?
So we're doing a lot of different things in DCOTS, ranging from chemistry to aerosol physics to small-scale dynamics to global-scale dynamics. But my personal interest in the project is really in atmospheric transport and mixing. And so if you've ever stirred cream into a coffee cup and you've looked at the beautiful patterns that you get as it mixes into the coffee, the same thing actually happens in the atmosphere, but at scales that are a million times larger. So these storms inject material, and I'm really interested in how that gets mixed and distributed all the way around the globe.
Cool. Well, that sounds very interesting as well. Well, thank you so much, Ken.
Sure, thanks.
We're pretty lucky today because joining us in the hangar is one of our NASA pilots, Dean Gucci Neely, who's going to give us some insights into what it's like to fly in that rarefied space on the ER2. Dean, take it away.
Good morning. Thanks everybody for coming out today. And as you just heard from a few of the principal investigators and the science teams on some of the campaigns that we have coming up at NASA, the aircraft you see behind me is the ER2. And that becomes the instrument of choice as far as a platform that can carry a large package of instruments from multiple teams that want to look down through the atmosphere from the top down. It's still the highest manned air-breathing aircraft in the world. There's 5 of us at NASA that fly this aircraft behind me. And what we're going to do to support this is take this up in a single-seat cockpit wearing this uniform, as you see, which I'll explain a little bit more why in a minute. But the idea is that we can take the package of instruments that are actually installed on the aircraft behind me up above nearly all of the Earth's atmosphere and look all the way down through it, studying what you just heard about with the DCOTS and impact science campaigns that we'll be looking forward to executing this in the coming months this year. In that environment, this is an inherently unstable aircraft, small cockpit, but we fly up so high that there's not enough pressure in the air to keep all the liquids in our body together. If we lose cabin pressurization, then all the liquids would boil, so hence the pilot has to wear this full pressure suit. So wearing a spacesuit up in that environment has its own set of challenges as well, but it's actually why the NASA pilots enjoy it, because we love a challenge, we love to learn, we love to explore. A few of the things about the spacesuit itself that I'm wearing right now, I'm dressed as if I'm ready to climb right into the aircraft. As we start to suit up into this, the first things that the pilot will notice typically is that you start to lose they take all your senses away. So you lose the sense of feel, can't really feel anything with the big gloves on here. As soon as I close this faceplate in a minute, then I'm completely pressurized inside. I have limited visibility, I can't smell anything, I can't hear anybody around me talking, and that becomes a challenge for some people, but we're well trained and experienced in this, and to the NASA pilots, we absolutely love it. This is just like another set of pajamas to me. And so what I'll show you in a minute is what this looks like as we inflate the suit, apply the pressure into it, which keeps everything in my body together in a high altitude, low pressure environment. And that's the challenge that we have, trying to be in this environment, be pumped up in a spacesuit and flying an unstable aircraft at the same time, where we've got to put these science instruments right over the point where the science teams really want to study what's going on in the Earth's atmosphere and how it behaves. So it's a fascinating science project that we're into here. It's an amazing environment to be in up at that high altitude. There's nothing like getting up there where you can look out over the distance and see the curvature of the Earth and that dark purple to black sky up there that we don't see down here on the ground because we have moisture that's filtering that. But that's an adventure and it's an amazing privilege, and we're looking forward to supporting these science campaigns studying the Earth's atmosphere and its behavior this year. Now, what I'll show you now, I'm going to seal up the faceplate and we'll turn the oxygen on, and I'll show you what this looks like pressurized, and then I'll hand it back to Samson. All right, time to get blown up. Okay, just like sitting down in the cockpit. We'll inflate the suit, and then I've got to fight against the suit to operate the aircraft. Okay, as this inflates, my mobility becomes very limited here, and I have to fight against it. To look down at different parts of the cockpit, I've got to pull the faceplate around. So this is the challenge I described, but we love it. It's a great environment to be in, and it's an awesome privilege to be involved in this study of the Earth's atmosphere. Samson, back to you.
Well, that's quite the demo, Dean. Don't get too comfortable over there. So we are headed from the top of the atmosphere back down to the ocean, because with me now is Tom Farrar, physical oceanographer with Woods Hole Oceanographic Institution, and also lead scientist for some mesoscale ocean dynamics experiment, or S-mode. Hi, Tom.
Hi, Samson.
So swirling currents in the ocean called eddies and their role in heat transport. Can you tell us a little bit more about that and how you're planning on studying it?
Yes. Well, the world's oceans are about 1,000 times wider than they are deep, and so if you were to zoom out and look at the Earth from outer space, the oceans are like a thin sheet of water covering the Earth, almost like a sheet of paper draped over the Earth. And because of this, the flow in the oceans is primarily horizontal at the largest scales. But the oceans are turbulent and they're full of eddies at all possible scales, from the largest scale, the scale of the ocean gyres, down to eddies just that would fit on the tip of your finger. And something interesting happens as we move from those largest scales down towards smaller scales. When the width of the eddies is similar to the depth of the eddies, you can have significant vertical motions, and this can be important for the transport of things like heat and nutrients. And we think this is important to heat exchange between the ocean and atmosphere, and to life in the ocean.
So, from what I gather, when you head out there in April, this is going to be a huge production. Do you want to describe some of the moving parts involved?
Yes, there is a lot going on in S-mode. We'll have 3 different aircraft making measurements from different altitudes. We need to measure a lot of things like the ocean currents, ocean chlorophyll, ocean temperature, and heat exchange between the ocean and atmosphere. So we'll have 3 aircraft, a NASA Gulfstream aircraft at high altitudes, a NASA King Air B-200 at intermediate altitudes, and a Twin Otter aircraft at low altitudes. And we'll also have a research vessel, an oceanographic research vessel, and a bunch of robotic ocean vehicles.
So a lot of effort going on here. What's the big payoff? Why such a big effort to put this experiment into action?
Well, the oceans can hold a huge amount of heat. If you took just the upper meter of the oceans and cooled that 1 meter of water by 1 degree and put that heat in the atmosphere, it would be enough heat to heat the whole planetary atmosphere by 1 degree. So the heat transport to and away from the ocean surface is really important.
Wow, in terms of the climate impact, I can see that.
Yes.
It'll help us move forward with those kind of modeling. Great. So, yeah, on a personal note, why interested in physical oceanography? We know people that study, dolphins, fishes. What interests you about the actual physical properties of the ocean?
Well, I've always enjoyed learning how things work, and I studied physics in college, and that was when I learned that there was such a thing as ocean physics, and so I became a physical oceanographer, and it's been so fun and interesting. I've gotten to go on ocean voyages all over the world and to work with people from all over the world, so it's been really a great career.
Wow, sounds like a lot of fun.
Yeah.
So we can't actually go to the ocean right now and see those instruments in action, but we can do the next best thing because our colleague, your SMOD colleague, Laurent Greer, brought a wave glider autonomous platform into the hangar. So do you want to go check it out right now?
Yeah, let's do.
Awesome. So the wave glider is going to be on the RV Oceanus, right? Oh, here we go.
Yes, the research vessel Oceanus will go from Newport, Oregon to the region offshore of San Francisco, and it will take about 2 days for the ship to get there.
Wow, and here's Laurent, who's actually going to be in the RV Oceanus. Am I correct, Laurent? Yes. Awesome. And so you are kind of manning these wave gliders, right? So there's several of them, and you'll be they'll be under your care.
Yeah,
That's
so
right.
we'll be driving them around, trying to keep them together. So we're going to have an array and making measurement at the same time.
So yeah, it looks like a very large surfboard with a lot of complex parts, and I imagine it cruising on the surface of the Pacific Ocean. Do you want to point out some of the measurements it's making?
Yeah, sure. So we're going to make measurement both in the air and in the water. So for example, this sensor is a weather station, so it's going to measure the wind speed, wind direction, air temperature, humidity, atmospheric pressure, rain. Another cool instrument is this 3D sonic anemometer, which gonna measure the fine structure of the airflow above the waves. In the air, we also have a bunch of GPS, which give us the position of the wave glider, but also its motion. And from its motion, we are able to retrieve the main characteristic of the wave fields, such as the wave height or the period of the waves. And then we have an ensemble of instruments underneath in the water. So these instruments allow us to measure the temperature, the salinity of the water from the surface down to above 150 meters. And along that, we also have a current profiler, which measures the current speed and direction pretty much from the surface down to about 100 meters.
Wow, that's a lot of capability for one platform. So I'm looking at the top, and it almost looks like solar panels. I'm just begging the question of how this thing moves. And I see fins, I see other things on here.
Yeah, so that's one of the cool things about the wave glider, is just use the power of the energy of the wave as a mean of propulsion. So, and the solar panel are just to charge the battery that we use to power the instrument and the control and communication unit. And so to give you the principle of operation is really simple. The float here stays at the surface, and the sub at the bottom, equipped with this fin, stays about 8 meters deep. And both of them moves up and down under the action of the waves. And with the help of these fins, this vertical motion is converted into horizontal motion, leading to the propulsion.
Wow. And so this is controlled by remote control back from the ship?
Yes, exactly, by satellite communication. So we know its position, its status, and the cool thing about it is that we do some real-time processing of our sensors, and we send them back to shore every 15 minutes an update. So we know the conditions they are facing, and we can adjust our operation of area and also our trajectory based on those conditions.
Wow, that's pretty high tech. That's incredible. Tom, this is just one of many instruments that are going to be in use on this campaign in the ocean. What is the special niche about this wave glider?
Well, the wave gliders and really the other robotic platforms that we'll have in the ocean will be giving us a view of the 3D structure of the ocean, and we're especially interested in the flow of water, so these will give us a 3D view of that water and how the eddies are swirling and the currents are coming together, leading to vertical motion in the ocean.
Cool. Well, that is very interesting. And we're working in combination with the aircraft to get measurements above, below, so it's a very 4D look at what's going on in these eddies.
That's right. The aircraft will give us a great spatial picture, but they're seeing just the surface of the ocean.
Right. Awesome. Thanks so much, Tom. Well, good luck with the wave gliders and good luck with being on that ship.
Thank you.
Laurent, and Tom, good luck with the entire campaign.
Thank you.
All right. So next we're moving on with my colleague Joe Atkinson. He's actually at Langley, and he's talking with some of the team members for our next field campaign we're going to talk about. It's called the Activate mission. It's the aerosol cloud meteorology interactions over the Western Atlantic. Take it away, Joe.
Hi, I'm Joe Atkinson, and I am at the Hangar here at NASA's Langley Research Center in Hampton, Virginia, this historic facility where Gemini and Apollo astronauts train to do rendezvous docking maneuvers, and where we keep our fleet of research aircraft will be home base for Activate scientists and crew when they begin conducting research flights out over the nearby and super conveniently located Atlantic Ocean just next month. I'm joined today by Luke Ziemba. He is the instrument scientist here at Langley for Activate. Behind us, you can see the Falcon and King Air aircraft that they will be using. When I look back at the Falcon, it has all these crazy probes and sciencey looking things sticking out of the top of it. What are we looking at? What do these things do?
So for Activate, we're making lots of different measurements, so we need lots of different probes and instruments in the aircraft. If we look at the crown of the aircraft, you can see 4 inlets. On the left side, as you're looking at the aircraft, is a gas inlet that we use to bring in air and measure the concentrations of CO, CO2, and methane in the atmosphere. Next over is an aerosol inlet that we measure the properties of particles in the atmosphere, so the optical, chemical, and microphysical properties of aerosols. Next over is what we call a CVI, or counterflow virtual impactor, and that rejects those aerosol particles, and we only look at droplets that enter the probe, and then we evaporate those droplets and look at their composition. And then lastly, we have a cloud water collector, and that collects droplets inside the clouds, brings them into the aircraft through tubes, and then we collect water samples in vials that we take back to the laboratory and look at post-mission.
We have some instruments on the wings here as well. Can you tell us what those do?
The wing probes measure the cloud properties. On the right wing, we have what we call a cloud aerosol precipitation spectrometer, or CAPS, and that measures the size of the droplets and the number concentration of them. On the left wing is a similar probe that's operated by DLR, and that probe measures the number concentration and size of droplets, but over a different range of particle sizes.
Oh wow, so we're getting onto the Falcon here, and man, I can see that it's pretty crowded, and you don't even have everything on here yet, right? So tell me a little bit about what it's going to be like.
That's right. So we're currently integrating the Falcon, meaning we're putting our instruments on. We currently have 3 racks on the plane, and we're going to have 3 more sitting essentially right where we are on the plane now.
And you have to have people on the plane too.
Right, so during flights we're going to have 2 pilots up front, but we're also going to have 2 scientific operators that will sit in front of racks and monitor instruments and keep them calibrated.
And what does the Falcon do during these flights?
So we're based out of Hampton, based here at home, but we're going to be flying out over the ocean. So we can do local flights out over the ocean, or we can go to Bermuda and back, or target different cloud environments. Our flights are about 4 hours in duration, and we fly from about 500 feet above the water surface up to about 5,000 feet. And we're porpoising between those altitudes constantly.
While you're doing that, the King Air is going to be flying too. So talk to me a little bit about what the King Air is going to be doing.
Right, so the uniqueness of Activate is that we have coordinated flights between 2 aircraft. So we're flying low, but the King Air is flying up at 9 kilometers, looking down on the scene with remote sensors, and especially with the new system that we have, a drop-on system.
You actually have a dropson here in your hands. Can you kind of explain to us what we're looking at here?
Sure. The dropson has a parachute on one end and it has sensors on the other. We measure temperature, pressure, relative humidity, and wind direction and speed with the sonde. We use a launcher from the aircraft, and it drops at about 11 meters per second, and we get a sounding of the atmosphere as it falls.
You have 2 other instruments on the King Air. What are they?
A research scanning polarimeter and a HSRL, or high spectral resolution LiDAR, on board. Those two instruments in conjunction allow us to retrieve the properties that we're measuring on the Falcon aircraft.
We don't actually have them to show you here, but we are going to take you to the lab to see the HSRL.
This is our instrument and how it's configured on the aircraft. This is a high spectral resolution LiDAR. So what we do is we send different color pulses of laser light out into the atmosphere from the bottom half of the instrument. Those laser pulses go into the atmosphere, and we collect that scattered light energy from the atmosphere with our telescope, and then direct that light into the various detectors in the instrument head. At the operator station, I can look at those various signals coming from all the detectors, getting information about the aerosols and clouds. Now, why that's important, you've already heard about the detailed measurements that the Falcon is taking as they're flying down low. Well, we're flying up high, and we're measuring, it's a remote sensor, so we're measuring from the aircraft all the way down to the surface. And we can combine those measurements from both aircraft to really get detailed information and dig into the science of how aerosols and clouds interact.
All right, so that was our behind-the-scenes look at what we're doing here at Langley to get ready for Activate. Thank you so much, Luke, and thanks to Dave Harper. Back to you at Armstrong.
Well, thanks for the report, Joe. There's a lot going on that aircraft, it seems. Well, joining me right now is actually the lead scientist for Activate. It's Armin Sarushian, atmospheric scientist out of the University of Arizona. Armin, thanks for joining us today.
Thank you, Samson.
So it looks like your mission is in good hands, according to that video, right?
Correct. So, as we all know, clouds are a common feature in the lower atmosphere, and they're not just beautiful objects to look at in the sky, but they play a very important role in our planet's energy balance because they're very reflective. But we don't fully understand how clouds work, especially how they form and how they evolve. And so we need to change that. And it begins with understanding how do you even make a cloud droplet. So the seeds of cloud droplets are these little aerosol particles, things like dust or smoke. And when we breathe, we're inhaling large amounts of particles, and they vary widely in terms of, what they're made of and their size. So it turns out that depending on the number and amount of particles you have, cloud droplets can have very different properties in terms of their size, their composition, and their lifetime. And this leads to varied effects on weather and climate. So to understand these complex interactions between particles and clouds, we need airborne measurements, and we need information below, inside, and above clouds all at once, and it's really hard to do this with just one airplane. So Activate embraces this approach, as you just saw in the video, to use two planes that will fly in a coordinated fashion to get all the information we need at once. So we will do about 150 joint flights over the next 3 years over the western North Atlantic Ocean.
So, Armin, what kinds of aerosols are we looking at in this particular campaign?
What types of aerosols? Well, there's a wide range of different pollution sources that impact the western North Atlantic Ocean. That was one of the reasons we chose this region, because we need a wide diversity in terms of emission sources and weather types. So we have biogenic emissions from plants, from the ocean, we have sea salt, we have biomass burning, we have dust from Africa in certain times of the year, and we have urban emissions as well coming off the east coast over the ocean.
So, I know we've had a few campaigns that were looking at these similar processes, aerosols and clouds. We've been off the coast of Africa, we've been in the maritime continent by the Philippines. And so it looks like we're having a growing compendium of these measurements. So what's the point of having all these different measurements taking place across the world?
Yeah, so again, the science of aerosol cloud interactions, what we are struggling with, the research community, is a general lack of statistics. There are so many factors influencing cloud properties that we just need more and more and more data in different regions that are there's different types of particles, different types of weather, and so having data across the world, and what's very special about Activate is just the sheer amount of flights we're going to do is very, very large. We're going to get about 1,200 hours of flight data, which is kind of unprecedented, and so we need statistics. And so combining all these campaign data and using Activate, it's really going to help the international research community.
It's incredible. So how did you get motivated to get into this kind of science? I mean, it's not something that people just stumble into, I'm assuming.
Right. So since I was a a child, I've always been fascinated and inspired by airplanes. So although I never pursued flying myself, I've just liked looking at them and being on planes. So one of the best parts of this research is not just being on the plane, but being able to steer the direction of flights and doing impactful research. And to sweeten it up even more for me, my background is aerosols, but my professional role model, my father, he's a hydrologist who studies precipitation. And of course, the link between aerosols and precip are clouds, which is the heartbeat of the Activate mission.
It's incredible. So following in your father's footsteps and your work informing the others' work, I think that's kind of beautiful.
Thank you, Samson.
Great. Thanks so much, Remy, for joining us. Good luck on that campaign.
Thank you.
So we're from small particles in the clouds to one of the largest waterways in the world. We're moving on to the Delta X mission, and we're looking at water flow and sediment to figure out why some parts of the Mississippi River Delta are disappearing and why others are not. And joining me to talk about that is lead scientist Mark Simard from Jet Propulsion Laboratory. Thanks for joining us, Mark.
Thank you, Samson.
So Mark, let's start with some of the processes that are at play at the Mississippi River Delta and how you're looking at those things.
Well, river deltas form along the coast. As the water from the river meets the slow-moving ocean, the water from the river itself slows down, and the sediments that it transports toward the coast actually deposit at the mouth of the river. And as those sediments accumulate, they build up soil, so elevation of the ground goes up. So at one point, the water will be sufficiently shallow for vegetation to grow. So vegetation will contribute to the further processing of the sediments, so it will help maintain the sediment in place and also potentially accelerate the capture of those sediments. And not only that, there's also an ecological process in which, as the plants grow, they produce organic material, which they inject in the ground through the roots, of course. And every year they just contribute, just like the sediment, to elevation of the ground in the deltas. So Delta X looks at those two processes. So the sediment transport and deposition, and the second one is the ecological part, which is the plant organic contribution to soil elevation.
Incredible. And for those of you guys watching NASA TV, that noise is a hangar in motion. This is a live working hangar, so don't mind that noise. Great, Mark. So let's think about all the ways that we can study these processes. What's going on in the field when you get out there this summer?
Okay, so Delta X basically uses NASA assets, a set of 3 instruments that are used to calibrate numerical models. Those models will simulate the hydrology of the system, so the water circulating through the channels and across the marshes, and it will also simulate the position of sediments and the plant growth. So we use 3 aircrafts, of which 2 are radars. The radars are used to measure the hydrology of the system in the channel network and also throughout the marshes. It will look at the propagation, for example, of the tidal wave propagating upward inland in the marshes. We have a third instrument that will look at the content of sediment, so the amount of sediment that are found in the water, and it will also look at plant productivity. And that third one is an imaging spectrometer.
Wow. Well, we know that a lot of people live around the Mississippi River Delta. Do you want to talk about the importance of this research for the region?
Well, most of the deltas, the larger deltas in the world, are sinking under current sea level rise. They are threatened. So they have to accumulate sufficient soil and elevate the ground to keep up with sea level rise. In the Mississippi Delta, we're looking at almost 10 millimeters of relative sea level rise. So that includes subsidence of the ground and sea level rise itself. So it has to accumulate a lot of sediments. So we see on the monitors now the loss of land. So those red areas are the loss of lands in the Mississippi Delta. So if you take this land area that has been lost in the last few decades, we're losing land at a rate similar to 1 football field every hour.
Wow. So, in other words, better understanding of what to expect in the future will help inform the planning.
Yeah, so that model that we're calibrating, once it's calibrated, we can use it to predict which parts of the Mississippi Delta will be drowning under sea level rise and which ones will survive. So that way we can actually use that model to guide and support potential restoration projects.
Oh, this seems like very fascinating work. Mark, how did you get involved in this kind of science?
So my background is physics, so I tend to like things that are complex. Not only is this system complex because of the constant, the perpetual dance between the ocean and the river, which comes in and out, but there's also the complexity due to the people.
Right.
I like people, and I think at this point science is sufficiently advanced so that it can be used to help people and care for the livelihood of those 500 million people that live across the world in these coastal areas.
Great. Well, thanks so much, Mark. I agree, it's important work. You know, one of the key instruments that is going to be used for Delta X is the Uninhabited Aerial Vehicle Synthetic Aperture Radar, UAVSAR, and it happens to be right behind us. Dean Neely is going to reprise his role as NASA pilot and talk about what it's like to fly these science flights. Gucci, take it away.
Hi, welcome back. So today, as you just heard a little bit about the science mission looking down at the surface of the Earth in all different parts of the world, the aircraft behind me is what was formerly an Air Force C-20. It's a Gulfstream G3. And if you look at the white pod over my shoulder here that's at the bottom of the aircraft, that is the main science instrument. That synthetic aperture radar is what we take up high in the Earth's atmosphere, where we can fly through a very precise path repeatedly and look at slight movements down on the Earth's surface, whether it's looking at topography changes, vegetation, earthquake fault lines, any movement there, glacier movements, volcanoes, that sort of thing. This instrument here, the radar pod underneath it, has been coupled to a special precision autopilot in the aircraft that NASA's heavily modified so that the pilots can repeatedly fly through a small 10-meter tube. Think of it as like flying through a soda straw, and put that radar looking at the exact same position repeatedly, whether it's a couple of days later or several months or a year later, and look at changes on the Earth's surface. And that's an amazing thing to do. From up in the aircraft, the way we operate that is the pilots will hand fly on the normal aircraft autopilot and maneuver into using some of the symbology we have tied to that radar pod to get the aircraft and the synthetic aperture radar right where they need it. And then we couple up that precision autopilot, and then the magic starts to happen there. And that's where the observation happens on the Earth's surface, looking at just minute changes down to a centimeter. And that's how we're able to study how the behavior of the Earth itself is going. From the pilot's perspective, it's a great opportunity to fly a beautiful business jet like this in a very different environment. So typically what we're doing up there is working as a team with a radar operator in the back and a mission director along with the two pilots, and we coordinate all the action again the objective is to put that radar right in the exact spot that we had previously put it on other missions, and we can compare that data. It takes a lot of skill. It's very frantic in the last few seconds as we fly into the tube by hand and then couple up that autopilot, but it's very rewarding when you get to see some of the final product and see what comes out of the study, as you just heard a little bit about there. All right, it's a nice opportunity not to have to wear a spacesuit in this one as well. As you can see, I look a little bit more comfortable here, and I have all my senses back, and I can eat and drink and that sort of thing. So we enjoy flying this, as well as all the other platforms that you're going to hear about today that carry these amazing science instruments as we study the Earth's atmosphere. All right, Samson, back to you.
Thanks so much, Gucci. Well, there you have it, folks. 5 campaigns spread out across the U.S. tackling a diverse set of science questions. But this is only the beginning. We want you to keep following us as we cover each of these campaigns throughout the year. We'll be posting blogs, photos, videos. We'll have Q&As. We'll be giving you as much of the action as we possibly can. Please follow us on nasa.gov/Earth Expeditions for all the latest. And also follow us on social media at NASA Earth and NASA Expeditions. Thanks so much, and see you next time.